Now that we know what a residual plot is and what to look for, let's do a problem that has context with residual plot, amongst other things. So a researcher wants to know whether cola consumption is associated with lower bone mineral density in women. She collected data from a random sample of women. She asked the women how many colas they drank per week and then measured their bone density. Now we've already seen this problem a couple times, but that's okay. So we want to first look at the two graphs. So I want to compare and contrast the two graphs. So I have a lot of students sometimes that don't know how to read which one's which, and that's where this example came from. So the one on the left is a scatter plot, and the one on the right is the residual plot. Now, by way of comparison, obviously these have the same number of points because they represent the same data set, and they're going to have the same x values for those points. So 0, 1, 2, 3, and so on. So the x-axis is actually the same. But what's different about them, sorry about that, is that the scatter plot will have a diagonal regression line, and all the points are kind of clustered around it. Whereas the residual plot on the right has a horizontal line down the middle of the graph, and the points are scattered above and below, but they're not clustered. They're kind of spread out. There you go, Saturn spread out above and below. All right, which is a good sign, right? Because we're not seeing a pattern in that residual plot. So do the data appear to be linear, judging from the residual plot? Well, yes, they do, and that's because it looks like somebody just kind of tossed the points up there, right? So if they look scattered and evenly spread out, which this does pretty well, then that means that the data were approximately linear. So since the points in the residual plot are randomly spread out, in other words, there's no pattern nor cone shape or horn shape, whichever way you want to say it, to the points, then the data appear to have been linearly related. All right, what is the sample size and how do you find it from the graphs? All right, so this came from a question in the notes at one point or in the worksheet. So I asked what the sample size was and it's not given in this output over here, which is super frustrating. What you have to do is actually count how many dots there are on the graph. And you can count it in either graph because they're the same data points, right? So this first dot on the residual plot is the same as this first dot over here on the graph, right down here. Right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's the sample size is 15. And you can count the points on either graph. So if I go over to the residual, I would get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's 15 dots there as well because they're the same 15 women that were sampled for their bone density and cola consumption. All right, now the coefficient of determination is available to us in this computer output right here. So you can see the R squared is 64.9%. That's the one. Ignore the R squared adjusted. There, that's the best symbol I can come up with. So ignore the R squared adjusted. R squared, which is the coefficient of determination, is 64.9%. So write it either as a percentage or write it as a decimal. It's good either way. And correct. Oops, I should have done that in green, sorry. So then, what about the correlation coefficient? Sneaky. All right, so in order to do that, we need to take the square root of R squared, but we don't know if we want the positive or if we want the negative. So we're going to leave it as both for a minute, and then we'll look back up on the problem and try to figure it out. So since r is plus or minus the square root of r squared, we're either going to use positive or negative the square root of 0.649. Now this is a big key. Do not use 64.9. That is a big no-no. A lot of students do that and they get the answers wrong. So don't do it. You want the square root of the decimal. So if the square root of the decimal, the square root of 0.649 would be 0.8056. So I'm either going to use positive or I'm going to use negative 0.8056. Well, now I have to go back and I have to look at the problem. Oh, and we better make a big note to ourselves because I'm going to tell you right now, a lot of people lose easy points by using the percentage instead of the decimal. So there's that warning. And now when we go up and look at our graph, we can see that we have a negative slope on this graph. You can also see it in the computer output when the slope is the number that is multiplied by the x variable. X for us is colas per week. So the slope is right here. It's negative 0.002889. We actually saw that this was the slope back in section 4.2, and we did this problem before to interpret the y-intercept, which is the 0.8861, and the slope. All right, so since that slope is negative, even if I had not given you a graph, you could still tell that you need the negative r value because your slope is negative. So either because of the slope or because of the graph itself. All right, now last but not least, let's interpret the r squared. Now the r squared is 64.9%. So that means that 64.9% of the variation that we see in y, which is the bone mineral density in women, can be explained by the least squares regression line. And that's what I wrote. So 64.9% of the total variation in the bone density among women, in other words, the y variable for this context, is explained by the least squares regression line. You'll notice, by the way, that for the interpretation piece, we'll use the percentage. But for up here, when we have to find the correlation coefficient r, we do not use the percentage. We use the decimal, 0.649. So they're both useful, but they have their different uses. So the percentage tends to get used more for interpretation. The decimal is used more for calculations.